Hey guys, guess what? I'm back. Had a question come up that raised some further questions and a little more investigation on my part. The fundamental question is, why do we even do flat frame calibration? Do we need to do flat frame calibration? And this picture that I'm showing you here, and we'll come back to this picture, is why we need to do flat frame calibration. Now, why am I talking about flat so soon after just releasing a video like within the last couple of days on flat frame calibration? It came about, first of all, because of a very thought-provoking question from John, plus my forecast for the next week. Clearly there won't be any imaging. That means we get a YouTube video. So the little thought spiral I went down incorrectly is I began thinking, why is it that we're modifying the master flat frame, which after all has a mean ADU level of 20,000-ish, if that's what you set your flats to. That's what I typically do. When our master bias, for example, has a mean ADU of 294, and the mean ADU of a dark frame at this exposure time is around 7. So we're talking about making corrections to an image that has a mean ADU of 20,000, and we're just correcting it by about 1 to less than 1%. Why is that even important? And that's what led me to question this whole idea. Should we even be worrying about calibrating a flat frame? Well, let's talk a little bit about what is flat frame correction. That is to say, when we apply a flat frame to a light frame, what are we actually doing? And here's a very, very simplified and therefore incorrect description of how the flat frames are applied. First of all, on the left here, we have the flat frame. Now, somewhere in the flat frame is some maximum value. Let's say it's at this pixel right here. Now, let's call that value that we would pull out of the image M. Well, somewhere else, everywhere else, there are values in this image that have intensity levels less than M, and I'll just point to an area over here in this off-axis guide or shadow. We'll call that L. Well, over here in the raw light frame, so this is an uncalibrated light frame, we have at that same location, there's some value V at this same location in the flat frame. There's some value V that's in this shadow. What we're doing in a simplified way to correct for the value, for the intensity at this location in the light frame, is to multiply the value in the light frame, V, by the maximum value in the flat frame, the entire flat frame, divided by the value in the flat frame at that same location as V. So we're multiplying the value V here by a number, M divided by L. Well, by definition, M is the maximum value in the flat frame, and L is going to be less than M, so this number is always going to be bigger than 1. At best, it'll be equal to 1 when we get to the same pixel over here in the light frame. We'll pull this value out, we'll multiply it times M, the maximum value in the whole flat frame, and divide it by the value of the pixel at that location, which is going to be M, and so we'll be multiplying by 1. So this value would not change at all. This value gets multiplied or scaled up accordingly to compensate for the shadow effect. And so that, in a nutshell, is what calibration of a light frame is with a master flat. In fact, if we go over to PixInsight, we can demonstrate that process using a simple pixel math expression. Here is a flat frame that I used and talked about in the last video on flat frames. It's a flat that was calibrated using dark flats. In this case, it had a dew shield, and I was calibrating some luminance light frames that I had taken, and this is one of those luminance light frames. And you can see over here there's this shadow of the off-axis guider. There's a bit of vignetting in the corners. If you're able to see it in your version of this video, there's some dust donuts in the frame. So there's various defects in this raw light frame that we want to correct with the flat frame. Now, I think in the interest of making the pixel math expressions a little easier to track, I'm going to go ahead and change the name of this to flat and change the name of this guy to light. And now we're going to implement that formula we just looked at by going into Pixel Math. I'll go into the expression editor, and I'm going to say I want the maximum value in the flat frame, all right, divided by the value at some pixel within the flat frame, and multiply that by the corresponding strength or brightness of the pixel in the light frame. And so that's our expression of M over L times V. All right, so we'll parse that. There's no errors down here, so we're okay. Now, I also want to have it create a new image so I don't overwrite anything. And that should take care of that. And so now we'll just execute it. So in effect, what we're going to do is a very poor man's correction of this light frame with this flat frame. And there's our result. I'll need to do a screen stretch. And here you go. Now, notice that the shadow here is gone. It looks like we've overcorrected a bit. Some of the vignetting is gone around the edges, so it is a flat frame. It did, that little simple formula did kind of do its job, although, as I say, there are some issues down here where we're overcorrecting. But by and large, we are effectively correcting for the distortion that our flat frames are documenting. And so that sort of confirms, if you will, mathematical relationship of what we're doing with our flat frames and when we apply them to the light frame. Okay, so as we saw in PixInsight, we can take this frame, apply this simple formula, and maybe not as well as PixInsight will do with the proper approach, not the simplified approach that I discuss here, but the proper approach, we can compensate for various image defects arising from our flat frame. If this is the formula we just went through, this is the correction for a properly calibrated flat frame. Now, what do I mean by properly calibrated? What I mean is we've taken out all of the non-flat related noise. So we've taken out bias, read noise, we've taken out dark current noise, we've taken out all the noise sources except those that are associated with the image defects arising from dust or whatever shadows in our optical train. What if we don't correct for that? Well, in this case, we have something like this, where now we have the corrected values for the maximum value in the flat frame, but there's some noise we haven't subtracted. Maybe it's the bias frame, maybe it's the dark current frame, the dark flat. And down below, we have the value elsewhere in the flat frame, but we also have, and I'll just for the sake of simplicity here, I'll call it the same level of noise, eta. And by the way, coming from the engineering world, whenever we want something to appear more significant than it actually is, we use Greek letters. So that way we have M plus eta divided by L plus eta. This represents a flat frame correction to an image, to a light frame, where we have not subtracted out all of the noise. What happens if we overcorrect? Well, in that case, we have a minus sign up here. It's the same idea. We've taken out too much noise. What's an example of that? Well, you might have a dark frame that you took for your light frame, say at an exposure of 200 seconds, you have a dark frame. And now you're going back to your flat frame calibration. You take out the bias and you take out that dark, but you forget to check the optimize button in the dialog box in PixInsight. And so it doesn't down convert, it doesn't scale down that dark for 200-second exposure for your flat frame, which may be, say, 1 second exposure. As a result, you're taking out more noise than there actually is in the flat frame. And in that case, you are overcompensating for the noise, and you'll have an expression something like this. Here's the critical thing, something else we like to do in the engineering textbook world. It can be shown that. We're not going to show it. We won't go through the math here. But it can be shown that a properly calibrated, the correction factor applied to the light frame, the raw light frame, is M over L. But it can be shown that M over L correction for a properly calibrated flat frame is always greater than the correction factor you would get from an undercorrected flat frame. All right, so if I don't take out the noise for the bias or don't take out the noise for the dark, the corrections I'm applying to and then I use that flat to correct a raw light frame, I'm not correcting it enough. I'm not multiplying it or scaling up that pixel value enough to compensate for the effect on the image that the proper flat frame is telling me I have to compensate for. Likewise, if I overcorrect and take out too much noise, it can be shown that the correction factor that I should be applying is actually less than the correction factor I would apply. So if I undercorrect the flat frame by not taking out all of the non-flat related noise from the flat frame, I will also undercorrect the light frame. Similarly, if I overcorrect, take out too much noise, non-flat related noise from the flat frame, I will overcorrect the light frame. Let's go back to PixInsight and I'll show you an example of this. Okay, so here are two flat frames. The one on the left is the so-called properly corrected flat frame where I have used dark flats. I have taken it with the dew shield. So this is the proper flat frame calibration. Over here is a flat frame where I've done no calibration at all. I've left the bias out. I haven't corrected for the bias. I haven't corrected for the dark current, and it's the same. And if you look at these two images side by side, as we are, really you can't tell the difference. And the reason you can't tell the difference is because what you take out of the flat frame in flat frame calibration is so small compared to the original signal that it doesn't even show up. And so as a result, these two flat frames look identical. But are they identical? Will their effect be identical? Well, that's where we want to go back to the images that we did calibrate, the M51 images. I'm going to bring up the M51 that's been properly calibrated, or calibrated, I should say, with the proper flat frame. And now I'm going to bring up the image of M51 calibrated using the flat frames that had no calibration whatsoever. All right, once again, these two images look fairly similar. Clearly, we've gotten rid of most of the vignetting in the corners and the off-axis guide shadows. It appears we've gotten rid of, I certainly can't see at this resolution, any residual effects of dust donuts, so it looks pretty good. Here's what we want to do. If what I just said is true, that if you undercorrect your flat frame, that means we are not fully correcting for the effects of the flat frame. That means if I take this image and I subtract this image, we're going to see some residual effects that we have not corrected for. So again, let's go back to Pixel Math. And we'll go into the expression editor. We no longer need this expression. And I'm going to take this light frame, which is M51, DF, DS, etc. And I'm going to subtract the non-corrected one, which is this. But I'm going to make another change here because it could be, it should not, but it could be that there's a pixel value over in the improperly corrected light frame, stack of light frames, that is greater than the corresponding pixel value over here in the properly corrected stack, and that would lead to a negative number. So I'm going to make this, I'm going to make sure we don't have a math problem here and call this, let me, the maximum value of this, or 0. In other words, we don't want any negative numbers here. The smallest number we should have is 0. All right, let's parse it. Okay, doesn't find an error. That's good. Now we'll go ahead and run this. All right, so now this is this image. So I'm taking this image here and I'm subtracting this image from it. And we'll see what we have left over. There you go. So if you look, everywhere it's brighter in this image on the left, that is to say, in this image back here is brighter than this image. Wherever we have a brighter signal over here, that means this image, or the light in this image, is greater than the light in this image. And you'll notice it looks very curiously simple to a flat frame. In effect, what it's saying is that the corrections that we've applied using the properly calibrated flat frame to the stack of raw light frames is greater than the correction applied with this improperly calibrated, this non-calibrated flat frame. And that's exactly what that little math equation was saying. With this image over here, we've used a flat frame that has compensated for the non-flat frame related noise. As a result, when we apply that flat frame, the scale factors that we're applying to the individual raw frames that make up this image, we're not scaling them up enough. And as a result, we have these leftover residual artifacts clearly associated with the flat frame, the shadow of the off-axis guider, the vignetting around the edge, the dust donuts that you see in here. So even though when we look at these two images side by side, we don't see those residual defects. They are in the picture, and it is possible in some cases they will be more prevalent and more obvious than others. But in this particular case, they don't jump out at you in this image, but they are there. Another thing we did in the video a couple of videos ago is compare the effect of calibrating flat frames using dark flats or using a master bias frame and a master dark frame that's been optimized or scaled back down to the exposure time we use for the flat frame. So this was the image we had of our M51 stack using the another nominally equal approach to calibrating the flat frames. Let's play the same game. Let's take this calibrated stack over here with the quote proper flat frame and subtract from it this image over here, which has also been calibrated with a, if not call it the proper, then an alternate flat frame calibration where we use the bias and darks as opposed to the dark flats over here on the left. So we'll go back to our pixel math, and we'll go into the image, the expression editor, and this time we want to take this guy out, and I'm going to substitute in this version of the M51 stack. Once again, we'll do parse, no issues, that's good, and we'll execute. Now over here, this is what we got when we subtracted the properly calibrated light frame results with the non-calibrated flat frames. So we subtracted two light frame image stacks, one calibrated properly and one under calibrated with the flat frames. This is the image we have by subtracting the properly calibrated light frames with another nominally equal calibration of the light frames, and here's what we get. There's nothing here that screams out as residual or artifacts of the flat frame like this does over here. In other words, there is some noise in here. There's some differences between these two images. We have done a good job, or both methods do a very good job of subtracting out the non-flat field noise, leaving us with a flat frame that does a good job of pulling out flat frame effects. So for all intents and purposes, these two images of M51 are the same. This one calibrated with dark flats, this one calibrated with a bias and properly scaled, that is optimized darks. And these both give us an adequate, if not equivalent, calibration relative to the flat frame. So what we've just illustrated is this relationship right here, where if we don't calibrate our flat frames, we are therefore not going to have a scale factor that will properly compensate our light frames, our raw frames, for the flat field effects. We have to calibrate and do it as accurately as possible, our flat frames, in order to get the right scaling factor. All right, let's just summarize where we are. Well, first of all, proper flat frame calibration is, in fact, necessary. Don't get fooled like I was fooling myself into thinking that, well, the bias signal and the dark signals are so much smaller than the flat signal. What's the point of subtracting a tiny number from a big number? We're not going to show up. And indeed, it doesn't show up. If you look at the two flat frames, one calibrated properly and one not calibrated at all, they look almost identical because, well, they are almost identical from a magnitude standpoint. What matters is the relative measures within the frame, the flat frame itself. It's the ratio of the maximum value in the flat frame divided by the value at some other pixel in the flat frame. That's the key thing. It's not that the image looks the same. It's this ratio of maximum to some other to the value or the intensity at some other point in the flat frame. If you don't eliminate the non-flat related noise from your master flat, you may still see some traces of dust donuts, vignetting, and off-axis guider shadows. Maybe the shadow isn't as intense, but it's still there. You can probably still see a darkened zone representing that dust donut or the vignetting or the off-axis guider. On the other hand, if you eliminate more than the non-flat related noise, now you're going to overcorrect, and you'll see brighter traces. Instead of an off-axis guider, darker off-axis guider shadow, you'll see actually a bright zone. And I've seen these effects in various of my images over time, and so this is what is happening. If I'm seeing a brighter zone where there should be a shadow from the off-axis guider, if I'm overcorrecting, I know that I've taken, what that's telling me is I have taken out too much non-flat related noise from my flat frames. Thought I'd just share these thoughts with you and see if it helps. Okay guys, clear skies, maybe. See ya.